Okay, good morning, guys. Sorry, my hair tie is the strangest thing. So today, we're going to start talking about infinite series. We're going to go through section 11.2 in the textbook. Get my coffee together here. And then we'll get started. So this is a big day. Infinite series are one of the main topics in this class and definitely one of the more intimidating topics in this class. So I want you guys to pay extra careful attention, take extra good notes. And let's make sure we get these basic concepts for infinite series well understood so that the later bits of chapter 11 don't feel quite so scary. So last week, we learned about sequences, right? We learned about this second object who's got a notion of convergence. The first was improper integrals. The second was sequences. This week, we're meeting our third object that has a notion of convergence, and those are called series or infinite series. There's some prerequisite notation. So capital sigma. This is the symbol you see floating around everywhere in a mathematics movie, except for the integral symbol when they want to scare the shit out of the audience. Usually you see it with a number down here and a number up here. And then there's something inside here, like maybe n over n plus 2 or something, you know? The thing that sits inside the capital sigma is a sequence. And what the capital sigma here says to do, the reason we use the letter capital sigma, that's the Greek S, is the same reason we use the capital S for our integrals. It stands for a sum. It stands for the word S-U-M. So we read this as sum n over n plus 2 from n equals 1 up to n equals 5. And that is, I should put the second quote down here, shouldn't I? Yeah, I'll do that from n equals 5. It's the same sort of idea as integrating from x equals 1 to x equals 5, the function x over x plus 2. And actually, you'll see on Wednesday, more explicitly, the connection between sums and integrals. But here, if I wanted to compute this sum, I would plug in all this range of n, so from 1 to 5, into this function or sequence and add them up. So that's 1 over 1 plus 2, plus 2 over 2 plus 2, plus 3 over 3 plus 2, plus 4 over 4 plus 2, plus 5 over 5 plus 2. Right? This sum right now looks like this. This is just a shorthand for this. And of course, you know, we could clean this up. This is 1/3 plus 2/4 plus 3/5 plus 4/6 plus 5/7. Then you could simplify more, but that's not the point. The point is just making sure you understand the notation. Can I see you using the thumbs up react? Who has seen capital sigma summation notation? So this notation. If you saw Riemann sums, you saw this. And in your pre-calculus class, everybody should have seen this. So pretty much everybody should have had some exposure to this. It's the same notation you use for Riemann sums. But it's okay if you forget a little bit. More generally, if AN is a sequence, then the capital sigma n from, let's say, 0 to 6 of AN would be A0 plus A1 plus A2 plus A3 plus A4 plus A5 plus A6, right? So the capital sigma notation is just a way of writing a big addition problem in a small space. So it says, take this thing and replace n with all the numbers between 0 and 6. And then the sigma says, add them up. So you're going to add up all of these things as n runs from here to here. The sort of sums we're interested in this class are not finite. So everything I've written on the page so far are finite series, finite sums. In this class, we're interested in infinite sums. So that's the first big hurdle, is what the fuck does it even mean to add infinitely many things together? There's a lot of big challenges here. What does something like sigma n from 1 to infinity 2 times 1/5 to the n even mean? What does it mean to say I'm going to take this thing, plug in all the values from 1 to infinity, and then add those up? I mean, that's challenging on its own. The next big challenge is, can we figure out when stuff like that is finite? Can we ever compute the sum of the value? So these are the main questions. And it's a lot like an integral, right? The sum from 1 to infinity of some stuff is very similar to the integral from 1 to infinity of some stuff. So there's kind of two separate questions here, in the same way that there's two separate questions when we were working with integrals. There's the question of, is this finite? And if it is finite, can I find the value? And here, the answer to the second question is even harder than it was in the setting of integrals. We saw with some integrals, we can determine whether the integral is finite, but we couldn't necessarily find the value of the integral. That sort of thing will be even more pervasive with series. So without further ado, I will define an infinite series for you. Definition. This is a lot like the definition of a type 1 integral. The infinite series and I'll usually use the symbol S for the whole series. The infinite series S, which could be the sum from 0 to infinity of an, is defined as a limit. As a limit of finite sums. So we say that the sum from 0 or wherever to infinity of an is the limit as capital N goes to infinity of the sum from 0 or wherever up to capital N of an. This is the definition. This is the object we called S. And the object over here, inside the limit, we call S sub capital N. And you should compare this. The integral from 0 to infinity of f of x dx being defined as the limit as r goes to infinity of the integral from 0 to r f of x dx. Very, very similar things, right? If you look at the series, the infinite series, sum from 0 to infinity, is the limit as n goes to capital infinity of the sum from 0 to n. And here you have the integral from 0 to infinity is the limit as r goes to infinity of the integral from 0 to r. Same sort of thing, and for the same sort of reason. Because this infinite series goes on and on and on forever, I can't actually do the addition. It never stops. But I can do this addition problem. So here S0, capital S of 0, sub 0 would be A0. Capital S sub 1 is A0 plus A1. Capital S sub 2 is A0 plus A1 plus A2. Capital S sub 3 is A0 plus A1 plus A2 plus A3. And remember the trick here, we're trying to understand capital S without any subscripts, this guy, which is supposed to be the infinite sum, A0 plus A1 plus A2 plus A3 plus A4 plus and on and on and on and on forever. Right, that's what we're trying to define here. So if this thing can be thought of in any reasonable way, this big infinite sum that goes on and on and on forever, it should be the limit of these things. Because as you walk down this list, the sum gets longer and longer and longer. Here, S sub n, which is this thing, is A0 plus A1 plus A2 plus A3 plus A4, going all the way out to AN. So if there's a reasonable way to define the sum of infinite length, it should be as a limit of these sums that get longer and longer as you go down. So the sort of intuition is that the only thing that makes sense is this, that the full infinite series should be the limit of the finite series. This is the finite series. This is the full infinite series. And as capital N gets bigger and bigger, look what this thing is doing. It's getting longer and longer. So if the full infinite series exists, if there's any way to make sense of it, it should be as the limit of these things. Here, the sequence S sub capital N is called the sequence of partial sums for the series S. So I'll give you a second to write. I know there's a lot of new notation. I want to remind you or encourage you to read the textbook, section 11.2. It's a very good section. It's written quite well. Many of the sections of the book I have complaints about, but not this one. Well, one complaint. They use a lowercase n for S sub n, which is very misleading when you write it like this. But overall, the section in the textbook is very well written and you should read it. All right, definition. We say the series S equals sigma n from, it could go from 0 or 1 or wherever up to infinity of an converges if the limit as capital N goes to infinity of S sub n, which remember is the limit as capital N goes to infinity of the sum from 0 to n of a little n, exists and is finite, i.e. the sequence of partial sums is a convergent sequence. So this is really, zoom back in a little bit here. This is one of the reasons we really need to study sequences before we can study series. First, series are built out of sequences, right? I'm taking the terms of a sequence and adding them all together. If you list them, if you list A1, A2, A3, A4, and so on, that's a sequence. If you add up all the things in that list, that's a series. So that's the main difference between a sequence and a series. A sequence is an ordered list of numbers. A series is what you get by adding up all the terms in a sequence. We say that the series converges if the limit of the SNs, the limit that defines the series, exists and is finite. And what does it mean to say that this limit exists and is finite? Well, it's the same thing as saying that the sequence Sn, not the sequence An, mind you, the sequence Sn converges. So a few things that people get their heads twisted up about in this section. The difference between AN and SN. The difference between AN and SN is right here. Make sure this got into your notes. Make sure you understand what this says. AN and SN are totally different animals. S5 is not A5. S5 is what you get by adding up the first 5 terms of AN. Okay. I'm going to teach you about 2 special sequences today, and I'm going to teach you one big rule called a convergence test. I'll leave this here just for a second. Anybody still needs to write. So the 2 special series I'm going to teach you about today, one of them is a geometric series, which comes from geometric sequences. The other one is called a telescoping series, which comes from like thinking about those old pirate telescopes. You'd land ho, and then and they would collapse down. Telescoping series are called telescoping because they collapse down in that same way that those silly pirate telescopes collapse down. Okay, moving on. Geometric series. So y'all remember what a geometric sequence was, right? A geometric series is one where the sequence being added up is a geometric sequence. i.e., a series S is geometric if it can be written as sigma n from wherever to infinity of AN, and AN is some constant times some other constant to the n. So AN is some constant A times R to the n. That's what a geometric sequence is. So a geometric series is a series, capital sigma, n from 0 to infinity, of A times R to the n. And this is a shorthand, remember, for the big long addition problem, A times R to the 0 plus A times R to the 1 plus A times R to the 2 plus A times R to the 3, and so on forever and ever and ever. So instead of just listing those numbers, now I'm adding them up. The numbers themselves are the same as they would be from a geometric sequence, A times R to the n. But now instead of just listing them and asking, does that list get closer and closer to something, I'm adding them all up. An explicit example would be something like 5 times 1/2 to the n. Which is 5 plus 5 times 1/2 plus 5 times 1/2 squared is 1/4 plus 5 times 1/2 cubed, that's 1/8, plus 5 times 1/2 to the 4, which is 1/16, plus, and so on. Now, if you don't know shit about an infinite series, besides the definition, besides what it is, there's only one way to try and figure out whether or not it converges and to try to figure out the sum. Anybody guess at what you should do if you wanted to try and start figuring this thing out? Yeah, I see something in chat here. Seeing if the corresponding sequence, so what sequence, Maggie? Depends on the sequence you're referring to. You're talking about AN or SN? So the geometric sequence here is the sequence AN. Turns out the convergence of the sequence AN is not super important for the series. There will be a particular theorem I'll give you a little later today that has to do with the sequence AN and whether or not the series S converges. But remember the definition of convergence for series S. It's all about the sequence Sn, right? The series S converges if the limit as n goes to infinity of Sn exists and is finite, i.e. the sequence Sn of partial sums is a convergent sequence. So what I should do is start messing around with the sequence Sn. I could find the first few terms of the sequence Sn. I could graph the first few terms of the sequence Sn. I could try to guess at the limit of the Sn's. So what's S0 here? Well, S0 is always A0. That's 5 times 1/2. S1, that's A0 plus A1. That's 5 times 1/2 plus 5 times 1/4. I'm going to pull up a calculator here so we can do this and this. So I can try to have both of these things running at the same time. God damn it. Okay, there's that, there's that. Oh wait, no, not the graphing calculator. I just want the regular calculator. A little more space here. So what I'm going to start doing here is computing the first few partial sums. The first one is 5/2, which is 2.5. The second term in the partial sum is 5/2 plus 5/4, which is 3.75.
Professor, wouldn't the first term just be 5?
Oh, it might be. Let me see here. Yeah, you're right. This is really S1 and this here is S2. So S0, thank you, is just 5. Yeah, 5 times 1/2 to the 0. Let me fix this. You should fix this in your notes too. Thank you. Yeah, S0 is just A0, and that is 5 times 1/2 to the 0, which is 5. S1 is A0 plus A1, which is 5 times 1/2 to the 0 plus 5 times 1/2 to the 1, which is 5 plus 5/2. And that's 7.5. So S0 is 5. S1 is 5 plus 5 halves, which is 7.5. S2 is the series going out to n equals 2. So that's A0 plus A1 plus A2, which is 5 plus 5 halves plus 5 fourths. So you come back here, say, okay, 5 plus 5 halves plus 5 fourths. That's 8.75. S3 is A0 plus A1 plus A2 plus A3, which is 5 plus 5 halves plus 5 fourths plus 5 eighths. And that's 9.375. Let's do one more. S4 would be A0 plus A1 plus A2 plus A3 plus A4, which would be 5 plus 5 halves plus 5 fourths plus 5 eighths plus 5 times 1/2 to the 4 is 5/16. Which is 9.6875. Maybe we'll do one more. S5 would be all of this it's the sum out to 5. So I'm not going to write the actual thing here. Oh, maybe I will. 5 plus 5 halves plus 5 fourths plus 5 eighths plus 5/16 plus 5/32. So I take this last guy and I slap on a plus 5/32. And I get 9.84375. So if you look at these numbers, 5, 7.5, 8.75, 9.375, 9.68, 9.84, do they appear to be getting closer and closer to something? The next term would be 9.921. The next partial sum would be 9.96. Here, the Sn appear to have lim cap n to infinity of Sn equals 10. And that's actually correct. This series does converge to 10. So that suggests two things. First, that the series S converges, and two, that the sum of the series is S equals 10. Now this approach kind of sucks, right? We definitely don't want to always do this. We don't want to have to always figure out our infinite series by writing out the sequence Sn and computing it explicitly. First off, I'm just guessing here, right? Like based on this list and the few extra ones that I did in the calculator, I'm guessing that these are getting closer and closer to 10, but it could be 9.999 rather than 10, who knows? And secondly, it kind of takes a minute, right? Writing all these things out, computing the sum of the finite series here, Sn, and then guessing at the limit. It's just not very rigorous, and it's not very fast, and it's not ideal at all. So what we're going to do instead is develop a result for geometric series that tells us exactly what's going on. And then I'll come back to that problem and I'll show you that we were correct. So we're going to develop several very important theorems on series, and this is the first one, the result on geometric series. So the theorem says that the geometric series S equals sigma n from 0 to infinity a times r to the n converges if and only if the absolute value of r is strictly less than 1. And that should look familiar. And in that case, S has value a over 1 minus r. And this works great for the series as it's written here. But you may have noticed me saying over and over again, n from 0 or wherever. The bottom index here, the starting value of n, doesn't need to be 0. Just like with sequences, right? Sometimes they start at 0, sometimes they start at 1, sometimes they start at 2 or 5. So the safer result, the way to remember the sum of a geometric series is it's always whatever the starting term is over 1 minus r, over 1 minus the common ratio. And this formula is only useful if you know the series converges. That is, if you have first checked that the absolute value of r is less than 1. In that case, yeah, Rakib, it's case, C-A-S-E. The proof, this is one of the few times we'll be able to prove directly what happens with a type of series, is that Sn here is A plus AR plus AR squared plus AR cubed plus the second to last term is AR to the n minus 1, and the last term is AR to the n. You can factor out an A, and you get 1 plus R squared plus R cubed plus R to the n minus 1 plus R to the n. And I'm saying to the because here these really are powers. So this is the nth partial sum of the series S above, right? It's the sum here as though it stopped at capital N. So what I'd like to do is take the limit as n goes to infinity of this thing. But as it's written, that's hard to do. I don't really know what this thing looks like as n goes to infinity besides saying it looks like the infinite series S. So first I'm going to do something clever. I'm going to multiply by 1 minus r. So if Sn is equal to this, then 1 minus r times Sn is equal to 1 minus r times this. And I'm going to bring the a out. So that's a times 1 minus r times 1 plus r squared plus r cubed out to r to the n minus 1, and then finally r to the n. And now I distribute this 1 minus r across this partial sum. Again, the a is going to hang out here. When I distribute the 1, I'll just get this thing back. So that's going to be 1 plus r squared plus r cubed all the way out to r to the n minus 1 and then r to the n. And then when I distribute the r, I'll have minus the sum. R times 1 is r times r is r squared, r times r squared is r cubed, and this will continue all the way out until you get to r times, the term right before this is r to the n minus 2, so that'll be r to the n minus, or r to the n minus 1, and then r to the n, and then r to the n plus 1. So I'm distributing the 1 minus r. This is what I get when I multiply through by the 1. This minus is this minus. This is what I get when I multiply through by the r. R times 1 is r. R times r is r squared. R times r squared is r cubed. And it goes on and on and on until you get to this guy. R times r to the n minus 1, that's r to the n. R times r to the n, that's r to the n plus 1. And now what you notice is that when you start subtracting these things, almost everything cancels. You get a times the 1 survives, but then you've got r minus r squared minus r squared, r cubed minus r cubed, all the way out to r to the n minus 1 minus r to the n minus 1. Okay, so that goes r to the n minus r to the n, that goes. You just get 1 minus r to the n plus 1. And this is really nice, because now I have no more dot dot dots. Now I have a nice finite expression. Not just finite, but like closed form, no ellipses, no dot dot dots. If you're having a hard time following the algebra here, don't panic. You're not responsible for the proof of the theorem, you're just responsible for using it. But understanding the proof of the theorem is a great way to understand what you're doing. So we'll have, if I now divide back over by this 1 minus r, on the left-hand side, I'll have just Sn. On the right-hand side, I have a times 1 minus r to the n plus 1 divided by 1 minus r. And recall that the full infinite series, S, is the limit as n goes to infinity of Sn. So here, S is the limit as n goes to infinity of a times, I'll write the brackets as parens, 1 minus r to the n plus 1 divided by 1 minus r. We don't need the parens downstairs. Now, r to the n plus 1, this is the same as the limit of a times 1 minus r to the n times r over 1 minus r. And this r to the n, we know what happens as n goes to infinity in r to the n. This piece will go to 0 as n goes to infinity if the absolute value of r is less than 1. So if r to the n goes to 0, then this piece is 0, and you just get a over 1 minus r. If the absolute value of r is less than 1. And the limit is infinity or dne otherwise. And that's it, that's the proof. Here, r certainly is not allowed to be 1. The case where r equals 1 in a geometric series is not convergent. It's makes the whole thing blow up to infinity. If r is bigger than 1, either like -1 or more negative than -1, or positive and bigger than 1, then this piece right here blows up to infinity. So the series, which is the limit of partial sums, we were able to compute the partial sums and find a nice simple formula for them. This is Sn right here. And geometric series are pretty much the only series where we're going to be able to find a nice formula for the partial sum. Now again, you're not responsible for the proof, but I do want to encourage you to rewatch the video, go back through this proof and see if you can understand it. See if you can follow the algebra, see if you can follow the logic. It's not terribly hard. And while you're not responsible for this proof, you will be responsible for doing similar things with what are called telescoping series. What you are responsible for from this is this theorem. Just knowing how this theorem on its own works. Not necessarily the proof, but you have to be able to recognize when the series you're looking at is geometric. You have to be able to figure out when they converge. And in the case where they converge, you have to be able to figure out their sum. Okay. So I want to return to the example that we started with. This guy. Here, I'll write him fresh. So the series we were playing with at the start was the sum from 0 to infinity, 5 times 1/2 to the n. And by writing out the partial sums, we were able to guess that this series converges and has value 10. Well, this is a geometric series. And r here is 1/2. So the absolute value of r is the absolute value of 1/2, which is 1/2, which is less than 1, plus the series S converges by our theorem on geometric series. Moreover, it has value, aka sum, right? When you add up all the terms, you get the starting term over 1 minus r. Well, what's the starting term? When you write out this series, the starting term is 5. And 1 minus r is 1 minus 1/2. That's great. 5 is 5. 1 minus 1/2 is 1/2. So this is 5 times 2 over 1, or 10, which is what we thought. I'll do one more quick example with geometric series. So I'm going to say I'm going to investigate the convergence of the series. And let's make it 2 minus 1/3 plus, what am I doing here? Say plus 1/18 minus 60 plus, shit, I suck. $108 and so on. So first we need to write this in sigma notation to figure out what it is. That's not entirely obvious. But to go from here to here, to go from 2 to negative 1/3, I multiply by negative 1/6. Right? 2 times negative 1/6 is negative 1/3. And to go from here to here, I multiply by negative 1/6. To go from here to here, I multiply by negative 1/6. So the ANs, the things that are being added up here, look like 2 times negative 1/6 to the n. And the n's here appear again to be starting at 0. So the series S is the sum from n equals 0 to infinity of the ANs, which is the sum from n equals 0 to infinity of 2 times negative 1/6 to the n. This is a geometric series. And the absolute value of R here is the absolute value of negative 1/6, which is positive 1/6, which is less than 1. So the series S converges and has value S equals the starting term, which is 2, over 1 minus the common ratio, which is negative 1/6. That's 2 over 1 plus 1/6. So the sign of R matters. If R is positive or negative, that will change this formula. 1 plus 1/6 is 7/6. So this is 2 divided by 7/6, or 2 times 6 over 7, or 12/7. And if you played that same game that we played with this first series, where you start writing out the partial sums, adding them up by hand, figuring out what the SNs get closer and closer to, the decimal representation of those numbers would get closer and closer to 12/7. So this is everything you need to know about geometric series. They converge if and only if the absolute value of R is less than 1. And in the case where they converge, the sum is 2 over 1 minus, or the starting term, not always 2, the starting term over 1 minus the common ratio. If the absolute value of R is greater than or equal to 1, then the series diverges, and it doesn't have a sum. Okay. 2 more important things before I let you go today. I know we're moving fairly quickly, but we need to because there's so much to do in this section. Theorem. This is your first real convergence test. You're going to have a bunch of convergence tests. This one's called the test for divergence. And Maggie, this is where we're going to connect to what you were saying when I asked that question, how can we start getting a feel for this series? Something about the sequence AN. This theorem, this test, simply says if the limit as little n goes to infinity of AN is not 0, then the series S equals sigma AN, summed from anywhere, I'll say from 1 to infinity, but it could be from 0 to infinity or 5 to infinity, automatically diverges. So in order for the series to have a chance at converging, the ANs, the things that you're adding up, need to get small. A warning. The converse is false. I.e., the limit as n goes to infinity of the ANs, if that is 0, that does not imply that the series sigma AN converges. So in Wednesday's lecture, I will give you an explicit counterexample. To come up with a nice counterexample, we need one more convergence test called the integral test. But yeah, there are lots of series that have the limit of the ANs being 0, but the sum of the ANs still failing to converge. Another quick warning while I'm giving these out. A mistake I see a lot is people saying that the sum from 1 to infinity of the ANs is equal to the limit as n goes to infinity of the ANs. This is super duper not true. These are totally different. Over here, I'm adding up A1 plus A2 plus A3 plus A4 plus A5 plus A6 all the way out to infinity. Here, I'm like finding the limit. I'm just taking I'm looking for the horizontal asymptote. So this is like the integral from 1 to infinity. This is like the horizontal asymptote. They're very, very different animals. Intuitively, so I want to return now to this test for divergence. Intuitively, this makes sense. If the ANs don't go to 0, say they go to 1 or 5 or something else, then the infinite sum of the ANs eventually looks like 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1. So a proof of the theorem, I'll just sketch really quickly. Suppose lim n to infinity AN equals L, and that's not 0. Then S, which is the sum from n equals, we'll say 1 to infinity of the ANs, which is A1 plus A2 plus A3 plus all the way out, on and on forever. We'll say plus AN plus A cap n plus 1 plus A cap n plus 2 plus and so on. The series, what I'm doing here is I'm splitting it up into the first few terms plus what we call the tail. This is like A1 plus A2 plus A3 plus, well, out here now this n is very, very big. So AN is very, very close to L. These aren't equal to each other, I should say, are approximately equal to, and this is now just L plus L plus L plus L infinitely many times. And that is the sum from 1 to capital N of a little n plus L times infinity. And since L is not 0, L times infinity is definitely infinity. So the series sigma n from 1 to infinity an diverges. The basic idea is that the convergence of the infinite series doesn't care about what happens in the first few terms. You know, you add finitely many things together, the result will always be finite. It's the tail that matters. It's the stuff that comes late in the series. If the limit of the ANs, the limit as little n goes to infinity of the ANs is L, that means AN is approximately equal to L for large N. Right? That's what it means to say the limit of the sequence AN is L. That when you look very, very late in the sequence, the terms of the sequence are close to L. So maybe these first few terms, I don't know what these are and I don't care. But these last terms, all the terms from some point on have to be very, very close to L. Remember when we talked about the definition of convergence for a sequence? The sequence AN having limit L means that from some point on, all the terms of the AN stay very, very, very close to L. So this guy is close to L. This guy is close to L. This guy is close to L. All the late terms in the sequence are close to L. And since this series goes on forever, there's infinitely many things here that are very, very close to L. So in your infinite sum, you have the start of the sum, the partial sum, plus the tail. And the tail is like L times infinity, because each of the terms in the tail is very, very close to L, and there's infinitely many of them. Now, any number times infinity is infinity if the number is not 0. If L were 0, then it's harder to say. That would be an indeterminate form, which is why the converse here is not true. But if L is not 0, then when you add L to itself infinitely many times, you definitely do get infinity. So the series would have to diverge. Okay, that's called the test for divergence. Again, not responsible for the proof, but understanding the proof will help you understand how to use the thing. An example where this theorem is useful is if I wanted to play around with the series, I don't know, say sigma n from 2 to infinity of n plus 1, or let's say n squared plus 1 over n squared minus 1. Okay, the first few terms of the series, we can figure this out. That's 4 plus 1 over 4 minus 1. That's 5/3 plus the next term, 3 squared plus 1, that's 10 over 3 squared minus 1, that's 8. And then the next term would be 4 squared plus 1, that's 17 over 15, and then 26 over 24, and so on. At a glance, it's not obvious whether or not this series would converge or diverge. It certainly isn't geometric. This is not like some constant times some other constant to the n, so I can't use my result on geometric series. So instead, I should try the only other thing I have, which is the test for divergence. which remember says that if the limit as n goes to infinity of the ANs is not 0, then the series automatically diverges. Well, here the limit as n goes to infinity of the ANs is the limit as n goes to infinity of n squared plus 1 over n squared minus 1. That limit, if you renormalize, you'll see is 1. Hopefully, having completed that sequence homework, you guys are getting pretty good at taking limits as n goes to infinity. And 1 is certainly not 0. So the series S diverges by, and I like abbreviations for these tests. They take a long time to write. So I'll say by TFD, the test for divergence. So far today you have 2 new big results, and they're on a new object. So in your notes towards the back, remember you should have a few pages dedicated to convergence tests. From today's lecture, you need to add 2 things. You need to add the test for divergence, which is this theorem right here. And you also need to add the result on geometric series, which is this thing right here. All right, so those 2 theorems, you need to add those. You need to begin your page of convergence tests for series, and you need to have the result on geometric series and the test for divergence. Those are your first 2 things. Wednesday, I'm going to give you a bunch more. And then Friday, you're going to get some more. And for the next couple weeks, you're going to get more tests to determine whether or not infinite series converge. Before I let you go today, I have one more thing to show you. Telescoping series. These are cool. There's no nice way to define them. Series in which partial sums have a lot of cancellation are called telescoping. And the way we handle telescoping series is by writing out the partial sums. And then remember that the full series is the limit of the partial sums. So you find a nice formula for the partial sum, and then you send capital N to infinity. There's a handful of famous examples. I'm going to do this one. 1 over n squared minus 1. If you start writing out the first few terms, it doesn't look like there's going to be a shitload of cancellation. This is 1 over 2 squared minus 1. That's 1 plus 1 over 3 squared. No, 2 squared minus 1. That's not 1. Sorry. That's 1/3 plus 1 over 3 squared minus 1 is 1/8. And then 1 over 4 squared minus 1 is 1/15. 1 over 5 squared minus 1 is 1/24, and so on. So I don't see any cancellation here, do you? Sorry, that's rhetorical. I don't expect an answer. No, there's no cancellation here. But I can factor the bottom. And then remember I said these series are a lot like integrals? If you wanted to integrate this, what would you do? You'd do some partial fractions. So that's what you're going to do here. You're going to set up some PFD for this. 1 over n minus 1 times n plus 1 can be broken down as a over n minus 1 plus b over n plus 1. And if you multiply through, you get 1 equals a times n plus 1 plus b times n minus 1. And at n equals 1, you get 1 equals a times 2, which implies a is 1/2. And at n equals -1, you get 1 equals b times -2, which implies that b is equal to -1/2. So that's the PFD. Therefore, the series S, which is sigma n from 2 to infinity, 1 over n minus 1 times n plus 1, is the same as sigma n from 2 to infinity, 1/2 over n minus 1 minus 1/2 over n plus 1. And you can factor out the 1/2. And you get sum from n equals 2 to infinity, 1 over n minus 1 minus 1 over n plus 1. The fact that constants pop out of series follows because the algebra rules for the sigma operator are exactly the same as the algebra rules for the integral operator. So splitting up over addition, subtraction, popping out constants, all of those things work just like they do for integrals. Now here, I write this as 1/2 limit n to infinity, capital N to infinity, sigma little n from 2 to capital N, 1 over n minus 1 minus 1 over n plus 1. Very similar to how we do our improper integrals. And again, the analogy between infinite series and type 1 improper integrals is a very deep analogy. And these telescoping series, we can actually figure them out the same sort of way we do our improper integrals. I'll have 1/2 lim capital N to infinity. And now I'm going to write this thing out. When little n is equal to 2, I get 1 over 2 minus 1, that's 1. 1 over 2 minus 1, yeah, that's 1. Minus 1 over 2 plus 1, that's 1/3. Plus, when little n is equal to 3, I get 1 over 3 minus 1, that's 1/2. Minus 1 over 3 plus 1, that's 1/4. Plus, when little n is equal to 4, I get 1/3 minus 1/5. Plus, when little n is equal to 5, I get 1/4 minus 1/6. Plus, and so on. But the whole point of writing this as a limit is that the thing here is now a finite sum. So I can't just go ... I have to write the last few terms as well. This is a finite sum. It only goes up to capital N. So the second to last term is when little n is equal to, I'll do third to last term too. I'll do little n is equal to capital N minus 2. That's going to be 1 over cap n minus 3. Minus 1 over cap n minus 1. And then I'll have little n is equal to cap n minus 1. That's 1 over cap n minus 2. Minus 1 over cap n. And then the very last term, when little n is equal to capital N, I'll have 1 over cap n minus 1 minus 1 over cap n plus 1. Close this, close that. So we write out the first few terms of the sequence, the first few terms of the series, and we write out the last few terms of the series. Because this series, the series at this line, is finite. And now my goal is to find a nice pattern, a pattern of cancellation. And what I see is that this negative 1/3 gets canceled by this positive 1/3. This negative 1/4 gets canceled by this positive 1/4. And in general, the negative term from a given negative piece from a given term gets canceled by the positive guy 2 terms later. So I have to ask myself, does this 1/2 ever get canceled? Is there ever going to be a minus 1/2 in here? I don't see one, so it'd have to be hiding in these ... dots. But if you think about the pattern, the negative guy gets canceled from the positive guy 2 later, or the positive guy gets canceled by the negative guy 2 before. But there is no guy before here because the series starts at n equals 2. So this fellow is going to survive, and so is this fella. The negative 1/5, well, what's the next term here? The n equals 6 term is 1/5 minus 1/7. So yeah, he's going to go. He gets canceled by the very next thing inside those ... dots. And similarly, the negative 1/6, he's going to go as well. He gets canceled by the positive guy 2 terms later. Now looking down here, definitely the n minus 1s cancel each other. And what was the pattern? That the negative term of a given, negative part of a given term gets canceled by the positive part of the term 2 down the road. So this guy is going to survive because the one that would cancel him would be the positive term coming after this. But there is no positive term coming after this because the series stops at capital N. So he's going to make it. And for the same reason, he's going to make it. But this guy and this guy aren't. This guy is the positive term that cancels the negative term in the last thing before these ... dots ended. And this guy gets canceled by the positive term 2 before in the ... dots. So finding this pattern of cancellation is a challenge. Yes, they will. Nick asked a really good question there. So how far did you have to look to find each guy's cancellation partner? To find the cancellation partner for this 1/3, I had to look 2 ahead, right? From the little n equals 2 term up to the little n equals 4 term. The number of terms that you need to look ahead is equal to the gap between the factors in the denominator. So the gap between n minus 1 and n plus 1 is 2, which is why you need to look 2 terms later. If this was like n and n plus 1, guys would be canceling with their immediate neighbors rather than 2 down the road. And if this was n minus 2 and n plus 1, then you would need to look for a gap of 3. So a safe rule is, in order to spot the cancellation pattern, first find the gap between the factors of the denominator. Here the gap between n minus 1 and n plus 1 is 2. And then always write at least 1 more term than the gap size at the start. So here my gap size was 2. I wrote 1, 2, 3, 4 terms at the start. And I wrote 1, 2, 3 terms at the end. Since my gap size was 2, I should always write at least 3. 3 terms at the start and 3 terms at the end. And that will allow you to spot the cancellation pattern. So I'll say it again. I want you to read the textbook because no matter what we do here, it's not going to be enough. We can solve all these problems, and still this stuff will feel overwhelming until you take the time to go through it slowly, reading the textbook, making your own notes, being very patient, thinking very hard. But I want you to have these examples in this video to look back on. So, what survived? The 1 survived. The 1/2 survived. Everybody else got a shit beat out of him until you get to the 1/n. He survived. And the 1/n+1, he survived. And as capital N goes to infinity, these two terms go to 0. So we get 1/2 times 1 plus 1/2, that's 3/2 or 3/4. So here, I would finish things up, and you must use the language here. The words, remember, are at least as important as the calculation. I'll say, thus, the series S equals sigma n from 2 to infinity, 1/n² minus 1 converges and has sum S equals 3/4. And this is not by any test or theorem, this is by the definition of an infinite series. S is the limit as cap n goes to infinity of the SNs. Because here we were able to compute the SNs. This thing right here is SN. Y equals 3/2. Why 3/2? Because 1 plus 1/2 is 3/2. So the limit as n goes to infinity of this curly bracket stuff is 3/2. So the 1/2 here is this 1/2. And the limit as n goes to infinity of all this stuff, the 1/n goes to 0, the 1/n+1 goes to 0, and you get 1 plus 1/2, which is 3/2. All right, that is all we have time for. I'm going to have to stop the lecture here for today. I know that was intense. This is a lot of shit. Okay, Zach, I think you should be in good case. I went through late last night and cleared everything out, but if you submitted it since then, I'll have to go back through and take a look. All right, so I'll say it again. Please read the textbook. We went through a lot of shit here today. We went through it quick. So I need you guys to go back through your notes right now. Don't wait. Don't wait, don't wait, don't wait. Do it now. Go back through your notes right now, the notes you just took, with your textbooks open, making sure you're going through and filling in anything that you have questions about, or putting little stars next to anything you have questions about. Those are the things you want to email, Canvas message, or come to office hours to talk about, but don't let them sit with you not understanding. Take care of this shit today. 11.2 is the foundation for all of chapter 11. If you don't understand this, then you're going to be royally fucked on exam 2. You don't want that. So take the time, put it in today, take the time and make sure you really understand the definition of an infinite series, the definition of the partial sums, the result on geometric series, the test for divergence, and then practice with some telescoping series. There are other examples in the book. The example I used here is not the easiest one, and I did that on purpose. There are some easier ones. And I want you to work with those on your own. All right, I gotta get running. I got another class, but again, talk to me in office hours, talk to me wherever you can, and I will be happy to help you. The lectures for Wednesday and Friday are pre-recorded. I have already uploaded them to YouTube, but I recommend watching them in order and in the normal way. So Wednesday morning, I would suggest watching the Wednesday lecture and so on. Between now and then, you should work on homework. So work on the first few homework problems, try to wrap your head around this shit, but only do that after reading the book. So read section 11.2, fill in your notes, mark questions you want to talk about in office hours, and then get started on the first few homework problems. The homework will be up very, very soon. All right, take care, guys. I hope you have a lovely rest of your day.